This is the second video in the completing the model of the atom unit. This video will cover learning goal 1b for the unit, the particle model of light. Looking at our learning goal and success criteria, learning goal for atom 1b is I understand the particle model of light. Now in this particular video we are not going to look at this first success criteria because we have covered that in class in our notes and our discussion. That success criteria being on the photoelectric effect and the explanations for why we see the observations we do. So this video will focus on the second two success criteria. The first of which here we will look at calculating the energy, wavelength, and frequency of an electromagnetic wave. And really we'll just focus more on energy because we've already spent quite a bit of time with the whole wavelength and frequency. So if we're going to quantify light energy, talking about calculating energy, one thing we do want to keep in mind is that we already do have one quantitative relationship for electromagnetic waves. That's that relationship between frequency and wavelength, which we know is c equals lambda nu, the speed of light equaling the wavelength times the frequency. But what we have learned now is that the frequency is also something that affects the energy of the wave and the energy of the photons in the light, to be more specific. So from Einstein's work, we learned that this relationship between energy and frequency is given by this relationship, this equation, where the energy of a photon, recall a photon is just a particle of light, so the energy of a single photon equals h times the frequency, where that letter h is a constant, which we call Planck's constant. Now I'm not concerned that you remember the name, but it was named after a physicist by the name of Max Planck. He also did a lot of work on this idea of quantized energy like Einstein did. The value of Planck's constant, and again, like the speed of light, you do not need to memorize this. I will always give this to you on any sort of assessment. It is 6.626 times 10 to the negative 34th, and the units on it, many folks will just interpret that as joules because the capital letter J is the unit of energy joule, and with the S on it, a lot of people will just think, well, it's plural, joules. But remember, with the symbols for units, we don't put S's on them to make them plural. That S is actually for a second. Okay, so this unit here is a joule times a second. And why there's a second there, or how it works out, we will see here in just a moment when we analyze the units. So speaking of that, unit analysis, if we look at this equation here, we can analyze the units that we would get from a calculation if we take Planck's constant h times the frequency nu, and we'll see what unit we would get for energy. So Planck's constant, as we just looked at, is the unit of joule times seconds. So joule seconds. Note that's not joules per second. Okay, if it was joules per second, it would be joules divided by seconds. So this is just joule seconds, or you could say joules times seconds. So we're going to multiply Planck's constant times the frequency. Well, we know that the units on frequency are hertz, which we can also write as 1 over seconds. So notice if we do that, we have a seconds in the numerator from Planck's constant. We have a seconds in the denominator from the frequency. So those seconds would cancel, and that would just leave us with a unit of joules, which makes sense because joule is a unit of energy, which that's what we're finding. Now sometimes you'll also see this written as a joule per photon. Now that being said, if you are doing this calculation, you could just list it as joule because it's understood that we're finding the energy of a single photon. We can see that there with the notation E with the subscript photon. Alright, so with that underway there, we've looked at the units, see how those work. Let's just take a look at a couple of example calculations. So again, like before, you'll see the problem written out there on your note sheet. Just fill in the solution as we go. So example number 1, determine the energy of a photon in a red light with a frequency of 4.2 times 10 to the 14th hertz. So this question is asking us about the relationship between energy, more specifically energy of a single photon, and its frequency. So we want a relationship between those two things. Well, that's just the energy of a photon equals h nu from the previous slide, which we said earlier is what Einstein came up with in explaining the photoelectric effect. Now notice this equation here is already solved for the energy of a photon, which is what we're looking for. So I don't need to do any additional algebra or any algebra period. I just need to substitute in my numbers. So the energy of a photon is equal to Planck's constant, and again, you do not need to memorize that. I will give that to you, times its frequency, which we're told is 4.2, times 10 to the 14th hertz. So plugging that into your calculator, you should get 2.8 times 10 to the negative 19th joules. And recall that unit analysis we just did on the previous slide, and we'll see it again here. Our unit check, I'm taking joule seconds in my Planck's constant, and I'm multiplying that by hertz for my frequency. So remember, hertz is the same thing as 1 over seconds, so my seconds cancel, and I'm left with joules. So the energy of a photon here is 2.8 times 10 to the negative 19th joules. And we've completed that question. All right, let's look at another example. A photon in an electromagnetic wave has an energy of 6.50 times 10 to the negative 17th joules. Determine the frequency of the wave. So like before, this question, we're looking at the relationship between energy and frequency. And so we're going to start with that same equation. The energy of a photon equals h times nu. Now in this problem, we are trying to find the frequency, determine the frequency of the wave. So I need to solve my equation for frequency. So just doing some basic algebra, we can see that we can divide both sides by h, and that will give us the frequency equals the energy of the photon divided by Planck's constant h. So now we can substitute in our numbers. Our energy that we're given of the photon is 6.50 times 10 to the negative 17th joules. And again, you may see that written as joules per photon, but we could just list it here as joules because it's understood. And then dividing by our Planck's constant h, again, that is a constant. You do not need to memorize that. I will give that to you. And we should get an answer of 9.81 times 10 to the 16th hertz. Again, consider your units. A very common mistake here is that students will look at this, they'll say joules cancel, which is absolutely correct, they do, but then the problem is they'll tell me that the unit of the answer is in seconds, but remember, seconds is in the denominator, so that is 1 over seconds, so that gives you hertz, just like we see here. And again, just keep in mind, the unit seconds is a unit of time, and so it wouldn't make sense to communicate our frequency in a value that has a unit of time. So that's why we need to make sure we check that. Now one thing you might be wondering here is how does this idea of wavelength fit into this? Because these two example problems we've seen here have dealt with the relationship between energy and frequency. Well, if, for example, in this particular problem, if we were asked to find the wavelength of this wave, we could find its frequency first here like we did, and then we could use the other equation, the speed of light equals frequency times wavelength, to solve for wavelength, and then we could plug in our frequency value. So we can see that frequency is the one quantity that relates, that's in both of those equations. And so we can use that to go between one and the other. All right, so go and pause the video and complete that check for understanding question number 1. All right, so you've had a chance to complete that check for understanding. You'll notice that you calculated a frequency and then you use that to find the wavelength, just like we said that was possible. All right, so looking at our learning goal success criteria, we have looked at how we calculate the energy, wavelength, and frequency of an electromagnetic wave. Now we're going to look at the last success criteria. Just like from the previous learning goal, we want to be able to order these electromagnetic waves by wavelength and frequency, but also now by energy. So this discussion here will focus on the energy aspect. So this is the exact same image that I gave you on the previous video. We have a depiction of our electromagnetic spectrum here, from radio waves, the longest wavelength, to gamma rays, the shortest. And then we can see that visible spectrum fits right in the middle with our Roy G. Biv there going across there, so we can remember the order of the visible light. Now, the question we want to address here is, what about energy? Okay, we know long wavelengths are here with radio waves, and the longer wavelengths means lower frequency, and the shorter wavelengths here with gamma rays are higher frequency, but what about energy? Well, if you think about that equation we just looked at, the energy of a photon, thus the energy of the light, is equal to Planck's constant times its frequency. So the greater the frequency of the light, the greater the energy. So that means the high frequency waves, the gamma ray end, this would be the high energy end, and then the radio wave end, okay, the long wavelength, the low frequency, would be the low energy end. Okay, so what I would encourage you to do is just focus on ordering by wavelength. So when you are working on memorizing this, just work on this order: radio waves, microwaves, infrared, then we get our visible, so that's the red, orange, yellow, etc. And then we got ultraviolet, X-ray, gamma ray. So just focus on remembering that order by wavelength. Longest wavelength over here with radio waves to shortest wavelength gamma rays. Get that order down, and then from there you'll just recognize, okay, here's my wavelength order. I know that the long wavelength is low energy. I know the short wavelength is high energy, and so you can order them by energy. All right, so keep this image up, pause the video, and go ahead and complete check for understanding question number 2 there, where you are doing some more ordering of those electromagnetic waves. All right, that completes this lesson on learning goal for Atom 1B. You can see the success criteria there. Again, our notes in class and discussion there hit up success criteria A, defining the photoelectric effect and explaining the observations. And in this video, we've looked at calculating the energy, wavelength, and frequency of an electromagnetic wave. And now we have looked at ordering electromagnetic waves by energy, wavelength, and frequency.